Hi, I'm Ben-Yaakov. This presentation is entitled Overvoltage and Overcurrent Protection, an example of a discrete design. Now, this presentation covers design steps of protection circuit to be built from basic element. What I mean by basic element, that is comparator, rather than dedicated IC. This is an engineering education video. It's not intended to be used as a reference for a commercial application. So here is the problem. We have a battery, we have a bus. There is a voltage on the bus, and we need to connect the battery to the bus. Now, obviously, you will connect the battery to the bus when the voltage of the battery is close to the voltage of the bus, very close to it. Otherwise, you may have very large current. So this protection circuit is protecting against this situation, and also whenever there is an overcurrent passing from the battery, it has to open the switch. So this is the switch. I'm not talking about the switch, how to implement it. I'm not talking about the current setter. I'm talking about this protection circuit. Now, this protection circuit is built from a current sensor that feeds the information to this circuit. And then there is a differential amplifier, which also I'm not discussing. There is a video in my YouTube channel discussing differential amplifier. You're welcome to watch it. This differential amplifier here measures the difference voltage across the switch so as to know whenever the voltage is safe to be connected, that is the battery to the bus. So this is this differential amplifier, and it is feeding this information to this protection circuit. Now, the command to turn on the switch is coming here, could be from a, say, microprocessor coming here, and this protection circuit, however, will not operate this switch if it's not safe, and it will open it if the current is too high. So here are the requirements. The switch is turned on when VC is on. VC is this signal here. Switch disconnect when the current is outside the range of, well, this is just an example, plus minus 100 amp. Once the overcurrent is tripped, the battery will not be reconnected again, even if VC signal stays on. That is, if there is an on signal and there is a disconnect, and due to overcurrent, and the current drops down, it will not reconnect. What you have to do is then to change VC to low. Okay, this has to be changed to low, and then to high again in order to activate the switch. And then VC will not turn on S, this is the switch, if the voltage difference across it is above some voltage. Here I put 0.3 volt, which is kind of reasonable. Now, if the connection signal is on, but S is not turned on, okay, so we have a signal coming in, the difference is too high, it will not turn on, then the battery will not be reconnected again, even if VC signal stays high. That is, if it is turned on, but it's not connected, and then the voltage drops, either the bus or the battery, it will not reconnect. In order to reconnect it, you have to turn this VC down to 0, and then you have to change it to low, and then change it again to high, or here it is. You have to change it to low, and then change it back to high. Now, also, I've set in an example that the response time of the protection circuit should be about, say, 5 microseconds, which for some application it's okay. And of course, this is just an example, an educational example of this design. Now, there are some safety precautions that has to be taken, and that is that we prefer that for operation signal should be high. That is, when signal is low, the input is low, the switch should be turned off. Also, if a device, say comparator, is not in place or is disconnected, or its output is shorted to ground, in all these cases, the switch should be turned off. That is, this is just a precaution in case of a malfunction of the circuit. And of course, we'd like to have a forced off state of the switch at power on. That is, when you turn on the system, you like the switch to be obviously in the off position. So now let's talk about comparators. Obviously, you need a comparator. You have to compare something. You have to compare the current to a reference. So the question is whether to use a open collector comparator. Well, this is not collector, it's a drain, but the name of this type of comparators is open collector. That is, there is a transistor here, and then there is a resistor pull up to the VCC, or to use a push-pull, which is just sort of sourcing and sinking current here. Well, since the requirement is that when the signal is off, that is low, you like the switch to be off, then you don't want this configuration, because if, say, there is no comparator here, something happened to it, it's been misplaced or disconnected or whatever, then you'll have a high voltage here. While here, if it is disconnected and you have a resistor to ground, it'll be zero. And this zero will be interpreted as a signal to turn off the switch. So I prefer this push-pull, and obviously I prefer a rail-to-rail unit. That is, that the common mode and the input and the output can be overall from 0 to the VCC range. This makes life a little bit easier because you are not restricted in the magnitude of the voltages. So here is an example of a, just one example. There are many comparators of a comparator that will do the job. It has, well, it's a low current. It has a rail-to-rail input, which is fine, 0.3 to minus 0.3 to 0.3, and it is CMOS compatible. We'll see that at the output it's also rail-to-rail, and the propagation delay is about 4 microseconds. The 4 microsecond is pretty good. Now let's have a look at the table here. We see the input voltage range is indeed from minus 0.3 to 0.3, which is just the full range. The input offset voltage is, well, 1.5 millivolts, and then up to a maximum of 7 millivolts, which is also okay for our application. It's not that sensitive. And then we have a built-in hysteresis, which is also pretty nice, like 3 or 6 millivolts. That is, if you have some noise superimposed, the hysteresis will take care of it. And then we have the output section, also from VDD high to VSS, just about 0.2 volt offset, which is okay. And then we have the rise time and fall time below 1 microsecond, and the propagation delay is typical to 8 microsecond, which is within the range that I've specified. Notice that this is given for an overdrive of 100 millivolts. Now, what is an overdrive? Okay, if I have a comparator, I have, say, the input, minus input, plus input, and say the minus is at a given reference here. And then the plus goes from low to high. Then obviously the output will go from low to high, but then there is a delay. This is the propagation delay. Now this delay is the function of this difference here over drive. That is how much higher than this reference you are getting to. The higher the overdrive, the faster will be the unit up to a certain limit. And we can see it here. This is the propagation delay. This is the input overdrive. This is value here. And as we can see that if overdrive is low, this 1 millivolt, then, well, it's pretty long propagation delay. But if the overdrive is, say, 100 millivolt, then we get to these low values of, say, about 5 microseconds, which is okay. Now, the requirement that after a fault, and if this is sustained, then it will not recover, calls actually for a memory device. That is, the system has to know that something happened and will not allow a reconnection unless VC goes down to 0 and then high again. So for that you need a memory device, which is like a flip-flop. And here I'm showing just in a possible embodiment here. We have a flip-flop, we have a reset, and again the reset is low. That is, when the signal is low, we want the output to be low. Okay, so this is why it's a inverting input. And then we need here a derivative here, actually, a differentiator, such that we look only at the leading edge. So the leading edge is turning this thing on. And when there is a fault, it'll turn it off. And since there'll be no signal here, then it'll stay off. And then, of course, you need to refresh it by another input. Okay? So we do need this flip-flop. Now, since we are going to have comparators in the system, well, there's no sense then to add another flip-flop, another element. Usually, comparators are coming in like 4 in a package. So probably we are going to have some left over. So we can build a flip-flop around a comparator. Okay? Now, the way we're doing it is that when the output is high, it'll lock itself. Okay, the high voltage will go back to the positive and it will be kept at the positive, that is the high signal. So here it is now. At the rise of the leading edge of the control signal, we'll get a pulse here. This will go high, it'll lock itself. Okay, now this signal has to be higher than the V reference. Okay, if the V reference is very high, this signal will not allow this flip-flop or the memory or the comparator to lock. Furthermore, in order to force it to the off state when the input signal is low, I'm adding here a diode, so when the signal is low, it'll sort of pull it down and it will make sure that the output is low. This is the one that goes now to the control of the switch. So here is an illustration how this thing works. If this is the reference, this reference here, and this is coming from the fault detection comparators, then if we have a signal coming in, a high signal, we got this pulse here, it'll turn on the unit. Here it is, and then the voltage will be high at this point. This is this V plus terminal, and this will be kept at the on. Now, when the signal is low, then it is, of course, bringing it back to ground. Okay, so this is the way it works when you have a signal coming up and down. Now, if there is a fault, then this signal will go high. Okay. And consequently, it'll terminate this command here, and therefore the voltage will drop down because this will be too high, I mean much higher than this, and the voltage will go down and it will unlock. So this is the idea of this comparator. Now we can add now this power on reset by having a capacitor, which is at the beginning, before there is a VCC, it is discharged. So therefore it is pulling down this point here and therefore making sure that the output is low. And then as this capacitor is charged, then it gets to a voltage at which the diode is reverse biased and therefore there is no conduction here. Now if VCC drops, this diode helps to discharge this capacitor so as to be ready for the next cycle. So this is the power on reset of the circuit. So here is the protection circuit that I'm sort of showing. we'll have a window comparators at which the sensed current and sensed voltage are fed to. That is, then we'll have two limits here, upper and lower limits. These will cause a change here, and there is an end circuit here. And here is this reference is a function of the output here. As we have seen before, it'll go up or down depending on the signal that we have here. So any one of these that will be low, they'll be low here. So therefore they'll be high here. And this will push the V reference to a high voltage and therefore unlock the comparator if it is locked, or anyhow prevent these signals coming in from clocking the comparator, because if the reference is very high, then these signals will not reach the reference. Now let me say a few words about the LT Spice simulation that I'm going to show. I've used a generic AND or NAND gate that they have it in LT Spice. I didn't find a model for a real device, and so I'm using this generic thing. It's kind of a strange thing. It has a logic level of 0 to 1, and there's no ground connection or VCC connection, and then any unused input is just ignored. So this is just to emulate a real NAND, but then I had to adjust the level because this is 0 to 1, and I'll be working 5 volts, so there is some translation here, which is not, of course, crucial to the whole thing. So here is the simulation model. Let me start with something that we already seen. This is the flip-flop comparator, okay, the locking comparator. This is the exact circuit that I've shown. This is the power on reset, and here we have the derivative here, and then we have here the reference voltage coming here to the minus side, and this is the comparator that I've shown, and here is the end. Now this end is coming from all these comparators, and these are for the two limits, okay? So in one case it's going to the minus side, I mean the measured current, in the other case go to the plus side, and therefore so when we are below a certain level or above a certain level, this will go low, and therefore it will go low, and here will be high. Unlock the flip-flop and will not allow triggering again until it will be relieved, okay? So this is the window comparator again. These are two comparators. I have a resistance to ground, so if this is unsoldered or taken out or misplaced or whatever, I'll have a low voltage here. And basically, again, this is just a window comparator between these two reference level. Of course, the voltage, the current has been translated to a voltage that is fed here. And here we see the simulation result. Now, this is the power on reset signal. This is the voltage across the capacitor, okay? These are the command signal, turning on and off the switch, okay? And here we see the output of the fault signal coming out of the comparator. Whenever it's high, it means that there is a fault, that is either the current is too high or the voltage across the switch is too high. And so therefore, for example, if I have here a coming control signal, here is the derivative, it doesn't reach this level, so we don't have an output. This is the output now. And here we see that whenever it's low, we got a level here, and it is showing out the signal. And here it is locking this part here so that we are not going to have any signal here because of this low voltage across the capacitor for the power on reset. And here we see a various situation. We see here that we got a pulse coming in, and then very quickly here we had a fault, okay? Suppose we connected the switch, current started to flow too high, so the fault goes on, so immediately this goes down. And here we have a case that there was a fault, it was corrected, and afterward we are turning on the switch, and indeed we are getting the output as we should have. So this shows how this circuit works sort of in general. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.